Hello everyone, this is Alice. Today I have a new job is to introduce our ICAX new space. Now recently we have set up this new center for ICAX. It's in these high buildings, very modern buildings. Actually the place is really located in the center of Zhonglin, where is the ICAX space. This is a new place for ICAX, is everyone's home. This is a place for the Chinese or China Innovation and Technology Center. Welcome you. Okay. Hello everyone. This is a place for ICAX exhibition here. Everyone can see that we have such a wonderful, fabulous, exhibition place. This was ICAX Connect World and Universe. You can see the moderators Paul, me, Martin, Fulan, Chris, and me, so all over the world host these talks every Friday. This was that place we exhibit all these speakers here, and we have everyone on this screen, everyone on this space. Here you see that this big exhibition here will have all the speakers' photos on the screen. I can tell you that since April 17th, we have 113, weeks. We didn't stop ICAX talks, from different places. We have about 200 speakers from 40 countries, and we also have the young scientists to be challengers and panelists join the talk. So totally we host a lot of people, and we have the audience is about more than 20 million people, from different places, even from Africa, even from some countries maybe you never know, but they all love science and science all benefit the world. So on ICAX, everyone knows that we want to use science and technology, connect the world and the universe. We did it. Come here, you can see that this was a long hallway with a gallery. You will see all these speakers. Everyone have a special introductions on this screen. So one by one, so totally 200 speakers. You can find your names and your talks and what you are doing here. And it's like a long walk hallway to the space. We pass all these doors. We got to the most highlight place. It's like a very special place. Okay, open the door. Okay, you will see our speakers here. We got highlight, speakers in this space. So this was, like a dream come true. Like ICAX really want to connect world and the universe, get all these speakers, everyone, get their own space. And here we see that we always have this one word is like ICAX connect the world and universe. And what we can do for the world and the universe, we use our science and technology. All these speakers on this hallway, on this gallery, you will see that you have the chance. You are helping the world. You are promoting the world into the space. So we see that we want more and more people can come in. We want more and more science and technology can put into the market to let the world get better and better. That's ICAX's dream. That's also this space. Yeah, we are dreaming to make it better. Here we came to the fourth floor of these big buildings. Here we can see that this is our place, our ICAX club. So here you see that big logos here. Everyone can take a photo, and you came to home. It's ICAX Connect the World and Universe. We're waiting for you. Here we came to the place for ICAX club. Actually, this was a very exciting place. Everyone can see that all the ICAX speakers was posted on this big blackboard. So everyone can find your name here, can find your picture here. Also, you're welcome to, stay here for a chat, even for some, very nice discussions, collaborations. And see this one, we want to have everyone from the whole world, the scientists who came to ICAX. So with ICAX, we also have some kind of interesting something of special design. Here you see that we have this big map was for the world map. So everyone speakers come over here. You can have a chance to sign your name here. Me, okay. I will be the first one to sign my name on this, ICANX vault. So welcome to ICANX Club and sign your name here. Hello, this is a place for ICANX outdoors. So here is a nice place, especially in this time. We can have a beer, so we can have a coffee, we can have a tea. Of course, we can have a lot of friends go together. This is a place for friendship. So yeah, we will see a lot of friends here. Yeah, here.
Hello, Alice.
Oh, hi, nice to meet you. Cheers for ICANX.
Cheers.
Hello everyone, this is Alice. Today I have a new job is to introduce our ICANX new space. Now recently we have set up this new center for ICANX. It's in these high buildings, very modern buildings. Actually the place is really located in the center. Hello everyone. I think everyone will enjoy this short movie. Actually I'm very excited because we make this movie just 2 hours ago. Yeah, we think this is a nice place. We need some very interesting, story to tell everyone. So from the very beginning, you know that this new place is ICANX Club. Our home is located in the center of Beijing, Zhonglin place. So it's very convenient to come here. And when you jump in, you will see our exhibition here, and you will go to this club, this lecture place, got to have a seat, get some outdoor events. So will be very, very nice. Welcome everyone to jump in, and welcome everyone come here, stop by and say hello and show something new and show something exciting. So that's ICANX. I think that today was a really big event because it's a new start. We say that every year we want to make something interesting. We make something exciting. I think this year we really have something interesting here. We really have something exciting here. And so I'm so glad today we have so many friends come over, even though we have a very strict COVID-19 control, right? Yeah, but we also gather, friend support. We have many people online support us. So yeah, it's a new start. I think welcome everyone to come over to ICANX Club and to this, a place to see everyone in person. And we hope we can host more speakers here. We can host more lectures, and we can host, many exciting stories here. So today, as an opening, I see, everyone should be very excited. So sorry, I turned the wrong button. Yeah, too exciting. Okay. Yeah, for sure. I need to introduce myself because many people ask me, okay, who is on the screen, right? Yeah. So it says that one not looks like you, but that's me, right? Exactly. This is Alice Zhang and Beijing, and I think this place is very close to Beijing University, just 2, substation. So it's very convenient to get here. So today I'm here excited to introduce this new session and these new stories. And this September, there's also the new semester. Yeah, we have this, people's on the September. We say that excited beyond the science. I think exactly, I explain what we are going to do. So in September, we're going to have 5 weeks, 5 talks. First, today is Professor Zhonglin Wang. Next week will be Nicholas Peppers, and the week after will be 2 young scientists who win the Young Scientist Award, last year. So they will deliver talk here. And afterwards, we will have, Anne was from Australia. And then last week, we'll have a big name from Switzerland who is doing for the soft robots. He's very famous for this kind of AI stuff, Brad Newson. So this was 5 weeks, on ICANX, and this September, we welcome you to stay with us. And every week, right, like this time. So today is a big opening of this center. So we have this big name. Yeah, so Professor Zhonglin Wang, I think if you are working in science and technology area, you never miss this name because Zhonglin Wang was one of the top scientists in the whole world. Many people, read his paper and cited his paper because he has a high citation, almost number one citation, in the world. And Zhonglin Wang was working in the area, in the nano area for more than 20 years, and he contributed a lot of kind of new things, and we follow his work. I think many people, if I didn't, miss the numbers, in more than 60 countries, right? More than 10,000 scientists and the group was follow his work. So Zhonglin was the best, scientist in the world, and Zhonglin was contribute always new things to us. That's very important. As a scientist, I think Zhonglin was the best demo. So today he's going to talk about his new story, and his very deep story for what he's doing, in last few years. And this is a very big breakthrough in the science. So Zhonglin, please. Yeah, welcome.
First, I'd like to give my sincere congratulations to this starting of this scientists club for the world. Science connect the world and the universe and possibly galaxy too. So I'm very honored and privileged to be a speaker here. And I want to congratulate Haixia. Is this open?
Yeah.
Okay.
You got closer.
Alice, for this wonderful work. I'm completely shocked by what she has done with this extraordinary group. Not only the amount of work, but also creativity, as well the gathering so many outstanding young scientists around the world. We are doing nothing but to broadcast the spirit of science. So what she has done through this platform is make sure the world expand to the world to every corner. So I'm honored to be here. Thank you for giving me this opportunity. I think my talk today probably sent a lot of people to sleep. But I will try to give you an in-depth discussion on this topic. Okay? So my topic have a few sections. Number one, why bother? We know Maxwell Equation for a long time. Why do we are interested today? What we can do today. So first one, expanding Maxwell Equation. Why we do it? So let's start from the experiment. The experiment is that, Maxwell Equation was established in 1861, first version, until almost 1897, get the final version we are used to today. So it's more than 120 years ago at least. So well established, so famous, so important. But we have some new observations. What's new observation? Is that we have a new technology called trouble electric nanogenerator, TENG, which convert Mechano-Energy into electric power. So you see the difference of this one compared to this one. This is rotation of circuits. This is movement of medium. Two are different. 120 years ago, we don't have this. So most of the theory will develop based on this initial discovery by Faraday, 1831. That's the first experiment. He showed that. So let me show you the detail here. Let me turn this off. Okay, you can see the difference here. So you can see that this one have low frequency, but output voltage is high. The operation principle is different based on the relative movement of the medium. In contrast, electromagnetic generator, which is dependent on a metal rod, cut the magnetic flux, give you the current. So both have different. This is a circular motion. This is the medium motion. This use magnetic field, this use electric field. Output voltage proportional frequency, current proportional frequency. So our power is frequency to the square. Here the voltage is almost constant. Output current is proportional frequency, so our power is to linear frequency. It's very different. So we have this new experiment. So even you have this new experiment, why the old theory did not cover this? So let's look at that. In MEMS, mechanical action can at a high frequency. How high? 1.18 megahertz. In such a frequency, TNG can work well. In such a high frequency, it has electromagnetic radiation due to medium relative motion. So, which forced me to rethink about the question, how do we look at the original equations to be utilized for our purpose here? So this is the second, first experiment show mechanical action can at a high frequency. Second one is this. If you have a rotation TNG, which is rotation, medium relative rotation. Rotations have an acceleration. It's not an inertial moment, okay? So this gives you a displacement current. You can lit up lights at a distance apart. And this was observed a few years ago, as we see that due to medium relative rotation, we have electron displacement current, which radiates electromagnetic wave. So therefore, lit up the lights. So which forces us to think the motion of medium can wirelessly deliver power. Can we include this part in the equation? Was this included or not? So this was the second experiment. The third experiment was recently, because if you have a design here, you slide one medium from this one to the other one, you'll be able to light up the light bulbs, which is a few watts. So therefore, you can really deliver power wireless to a distance due to medium motion. Okay, so this is the third experiment. Another risk experiment is that if you have used the physical motion, you trick a piece of plastic, the electromagnetic wave radiated in 10 meters apart, be able to receive wireless. So the two means what? Medium motion can deliver power, can deliver signal to a distance. Okay, so this is the discovery. You can think some discovery more than 180 years ago. That time, they observed some phenomena. Later on, develop theory and derive more exciting application up to now. So this is the third experiment. The fourth experiment is this. This is underwater. Underwater. This is you talking your voice, you trigger a TNG. There's no power supply. It's different from this. This is have power. When I'm talking, this amplify, but this have no amplification. So voice trigger TNG give you a wireless signal which displays current, which transmit to the electrode here. Under the water, it can transmit a few meters distance away, receive here, control. So this is a motion triggered electromagnetic radiation. Motion triggered, not a current triggered. So this is due to motion. We have the, you can see here, okay, let me see. Can see the voice or not? Okay. Oh, you cannot hear. This is a TNG. This student talked to TNG. His voice triggered and generate displacement current under the water. This is the receiver, and then use this to control the light. You can see control voice into displacement current and transmit the distance and do the control. So this is the one of the experiment. The other one is same here. Use hand. So you padding. Use motion. You generate signal, and here underwater transmit a few distance. So don't look at this a few meter distance. In the future, we can get far. So let's start to think about it. Why the medium motion can give electromagnetic radiation? Can we include this in the equations for that? So this is an experiment. The other one is that they do truly underwater, and in a big, not a swimming pool, is an experimental pool. And they can trick the TNG, the voice trigger here, the TNG signal meter wave can receive the signal here. So we really did this experiment, show that due to medium motion, you can generate electromagnetic radiation, and at distance, you can receive wirelessly. So I just give you a few experimental examples to show, we have to think about the questions. Let's look at, is there any possibility, was this included in the original equation or was not? Okay, so let's look at the theory. In the theory, it says on electromagnetic generator, use a metal coil cut through magnetic flux. So this is called circuits. Circuits motion give you a conduction current you receive. And this conduction current is all what we use today. Okay? But the current have two types. One is the conduction current. The other one is called displacement current, first proposed by Maxwell, 1861. And what's the difference? The conduction current is the current flow in a wire. So you can see, but the flow speed cannot be speed of light because the electron mass. So it can be a fraction of the speed of light. But this one is transmitted at the speed of light. So therefore, what's this displacement current? Is not a current due to electron flows, but a time variation electric field plus a medium polarization term. So it must be a time variation of electric field, must be a medium polarization term. So this is what was, we know that from many textbooks. Okay. So, but the thing's different now is this. The medium started motion. You can see this one in our case, and this is two medium can relative motion, and this motion can give you some additional things here. But this motion was not included originally in this equation. And the boundary condition was not included. Okay, so let me explain to you step by step. So this was the beginning. We think about, should we relook at the equation and see how can we quantify the output power of the TNG through the new terms we introduced. So let's give you the history, the second part, history of Maxwell equations. And this is a very important part of the thing. Maxwell first proposed the equation in 1861, but it was not in this format. This was the final format we use today. So this is called the integral format, and this is differential format. Basically have 5 equations. First one is Gauss's law for electricity, Gauss's law for magnetism, Faraday's law for electromagnetic induction. So this is the one, and Maxwell's law for Ampere's law, but this is displacement current. Lastly, conservation of charges. So this is the 5 equation we know. So when he first proposed this one, which was not looks like this, looks like this. One equation turned out to be a few. One equation turned out to be a few. This was 1861 Philosophy magazine published that. Okay, so this is a revolutionary theory. First one, which unifies space and time. Find that the electricity and magnetism can be unified. Okay, through this question. And light is an electromagnetic wave. And the proposed displacement current. This is a gigantic contribution of Maxwell. That time, which is mathematically, he proposed this one. Why he proposed this one? Because this 4 equation has satisfied conservation of charge. If you don't have this term, this 4 equation does not satisfy the conservation of charge. So he has to do that. But it was turned out to be was only a mathematical introduced in the first place, but turned out to be a big discovery. Our biggest discovery. But that was only until many years later. But when he first proposed this was in 1861. Okay, so this was the beginning. But many scientists contributed this one. First one, there are few scientists expand this one. This is Larmor. Larmor expanded it in 1897. 1897, Maxwell already died for almost 20 years. He died in 1879. It's almost 20 years. And he explained as a displacement vector is the field applied plus a medium polarization. He expanded this one from macroscopic scale to micro scale, atomic scale. So basically, it's a field you apply and a medium have polarization. Both add up on this one. This is what we use today in textbook. Okay, this is what we use in textbook. So this is the first one. Second one was experimental work. You had proof was true. George Fitzgerald, a British scientist, he first introduced scalar potential and observed oscillating current can produce electromagnetic wave. Oscillating current. That's what we use antenna. You know, all the satellite, the antenna we use for cell phone. use this oscillation. Then is Oliver Lodge, British scientist. He introduced electromagnetic resonance can be produced by arc discharge of a capacitor. All these are important landmark work for our application today. So you can see all this done very many years ago, step by step. Most important contribution came out by two scientists. Number one is that Oliver Heaviside. He was a British scientist. He unified the Maxwell equation to the very neat format we all used in textbook. And so this was done in 1885. He unified this 20 equation to 4. Most revolution contribution is Hertz. All this statement theory, who knows is true or not? Hertz proves 1888 experimental proof the existence of electromagnetic wave. Before that time, electromagnetic theory by Maxwell was not accepted by the academic community for more than 20 years. It was only say, well, until experiment verified by Hertz. So it's a long history for that. So this was the history of Maxwell equation we utilize today. And when we use this one, we all based on this landmark work by very many scientists. Okay. Now the question is, what are the assumptions on which the Maxwell equation was derived? Was it exact or is have approximation? So let's look at that. If you look at textbook, the textbook did not tell you this one. They just always call the equation as I just introduced. This is Jackson's classical electrodynamic book. And also, this is the most recent book that give you, just use this. So most case, they didn't tell you how would this derived. Just take as is. And most of us is take as receive. So without go to detail how it's derived. So I have the need to explain my experimental observation. I need to go to the detail. What was the assumption made for this one? I found that, if you look at the book by Feynman, and he, in the table 18.1, this is a differential form of electromagnetic induction, and this is the integral form. He said line integral of E around the loop equals the negative of the flux to B through time derivative. If you put a mathematical form is this. So this is the Feynman's put in an integral form and a differential form. Okay. So he says the flux, the changing rate of the flux is the circulation of electric field around this loop. Okay, I'll come to this in detail. So if you look at the book, this tells you just briefly the integral form and the differential form. Okay, in his famous lecture on physics, he gave a few examples. The first one is the one obeys this flux rule. This is the Lenz's law. He says the change, the rate of the flux change rate is the electromotive potential. So this was what it means. So he used this linear circuit. It's a linear line circuit. That means a line, like our wire is a line. And these wires show, yes, this is correct. But he gave 2 examples in his book, which he called Anti-Flux Rule. In the first example, you have a disk. This disk is rotating. He found this case does not follow this rule. And the second case, you have a 2 half of this segmentation of the circle. If you do rounding back and forth, he found that this also does not obey this law. So he gave 2 examples, but the book did not tell you why they did not observe the rules. Okay, so that's what the book says. But if you look at more details, so what's the difference between this and this? This is a thin wire. This is a disk called medium, rotation medium. That's the difference. So let's look at the details. What's the difference between 2? So you see my talk is motion medium. Motion medium with acceleration. This is the case. Motion medium. Let's look at those cases in the detail. So this is what we read in the book. So I put the 4 equations based on the physics law from the documentation given to us. First law, Gauss' law for electricity, Gauss' law for magnetism, and electromagnetic induction, as Feynman gave to in his book. Okay, then this is the Maxwell equation. So now this derivative can be applied to the field. It can also apply to the surface if the surface is changing. Okay, if the media is moving, the surface is changing. So this time derivative has to apply to this and here. But in most textbooks, they say, oh, if the medium does not change, you can directly apply the derivative to the field. So you have this. You switch integral and diffraction, but based on what assumption? Station medium with fixed boundary and volume. That's what it means. So then you get, from Stokes' law, you get this differential form as we're familiar with. So this was assumption made, but most time the book did not write the section where it come from. We just take from here. All right? So most of the students take as this exact. However, look, this another term is not there. Okay? Why do we have to consider? Because we observe the medium motion. Medium change can give you electromagnetic radiation. We need to include it here. So that's why our discussion based on this. Then you see some people say, well, in the textbook we already have used the Leonard-Windchurch potential. Leonard-Windchurch potential is that if you have a charged particle, it's a point charge, which move on a trajectory like this, you can calculate the scalar potential and the vector potential exactly. That's true because this is the point charge. Point charge is not a medium. Mediums have a shape, have a boundary. So point charge, you can express delta function, and the current can be a velocity of the charge movement plus its position. You can substitute here. You calculate. This is calculated in the accelerator. You know the accelerator for electromagnetic radiation? Light source is based on this principle, but it's for charged particle. It's not for medium motion. So many people say, well, you can do it this way. Under a condition of point charge, you can do that, right? So this is the condition that under which we can calculate for that. But if you have a medium, have shape and size, you cannot do this way. You have boundary condition for that. So this is not the case. Can cover what do I care about that. So this is the second one. So relativity. Relativity goes this. Let's say you have an electromagnetic phenomena. You have another observer. If the observer are moving like this, constant velocity, straight line, that means inertia frame. Inertia frame. So let me do this again. So you can see constant motion. This is the theory. Also in a vacuum, observer are moving. In a vacuum, the speed of light is the speed in a vacuum. Right? So through which, what he observed compared what you observe here, they give you a relationship. This is the Lorentz transformation. You can do that. So this is the we know that from textbook. So when you have medium motion, textbook immediately said, go look at that. But this is the condition what? Constant velocity, straight line. So if you do this, well, it did not cover. So therefore, for our case, we have a rotation, we have oscillation. That is called non-inertial frame. We have to reconsider the situation. So this is the special relativity we talk about here. Okay, so most of physics law say was developed in the inertial reference frame, and that means a reference frame that does not undergo acceleration. Okay, physical phenomena are the same when viewed by two observers moving with a constant velocity related to one another. That means you see one thing, I see the same thing, but I move away. What's the difference between you see and I see? If I move fast, there's a difference. That's what the special relativity talks about. But if I move like this, but you said, I will definitely see something different from you. Theory, special relativity does not cover that part. That's the difference. Okay, does not cover that part. So we have to be very clearly tell you we choose inertial frame for this case. Okay, what are we looking for? We on the Earth, we're looking for many moving objects have a boundary. What do I see? What do I see? They can have acceleration, they have different trajectory. What do I see? In such a case, you can analogize like this. You see in the house that's have something flying, something moving. What do I see? All can along different trajectory. So for the phenomena we observe on Earth, can we develop a proxy method which can cover this? So that's my motivation doing this. You can see my motivation is to cover something which is moving, but what do I see on the Earth? Okay, so I limit my discussion on engineering application, not on a unified universe, no, on the field in the universe. Limit my discussion on engineering application, on our daily life, on engineering. Okay, so that's the one. All right. Now let's look at how do we do it. We know the limitation, we know the approximation. How do we do it? That's the question we need to develop. So we call develop the Maxwell Equation for a Mechano-Driven things doing mechanical motion, which drive immediate motion. Okay. Theoretical physicists do this. They say based on the four physical law on the station medium approximation, give you differential form. So this station medium. Then they use Lorentz transformation to get this. Remember, this is for a constant velocity along the straight line. Most time in vacuum, if you have a medium, things become complicated. I'll discuss this one toward the end because medium have a dielectric constant, have a size, have a shape. How do you consider that? This is the theoretical physics discuss. So in our engineering application, we use Galileo space. That means space and time are absolute. Okay. In such a case that for engineering application, we can derive with for low speed motion, the field I observe on Earth, a moving object, give you like this. Under two assumptions. Number one, low speed motion and a non-relative speed approximation. That's good enough for on the engineering problem. We care about that. At the end, I will discuss the approximation on which it is valid. Okay. So this is two approach. Approach number one, approach number two. On this number two is what I take. At the end, I will discuss both. So if you look at the four physics laws, the first one, one of the key to understand use flux, 通量, flux, magnetic flux and electric flux. That means the integral of electric flux on a full circle, full surface is the total charge inside. The full surface integral, closed surface integral is the magnetic moment inside. That's zero, means no magnetic monopole. The third one is electromagnetic induction, is the changing rate of the flux through an open surface is electric circulation around its edge. This is the edge, 边缘. This is the circulation. This is the changing rate of magnetic flux. This is the same thing. This is conduction current. This is the displacement current. Is the changing rate of the electric flux through an open surface. Is the magnetic circulation around this edge. That's what it is. Okay, so if you use word to express this one, that's why math is the language for science. You can explain what I just said exactly like this. Math is the language for science, can exactly to express. So this can apply to the field, can also apply to the surface. Now let's do that. So calculus can apply to here. If there's variation, you can see this surface is expanding or moving. You need to apply both. Use two mathematical identities. I will not prove this mathematical identity. This mathematical identity assumes there's no structure change in a circuit. This circuit can expand and contraction, but not sliding, one sliding against the other. Okay? Because I will talk about the Feynman's case at the end. In such case, even for a general velocity, This velocity can be xy function. This equation give you this identity. This equals that, and this equal that. I will not explain detailed here, but just tell these two mathematical identity. I remember I submitted a paper for review. One referee said, "Well, this is velocity has to be constant." I said, "No, it's a general theory for field theory, right?" So if you meet such a referee, so reject because this only applied to. He did not get it right. Right. So this is. I use this one because I need to apply this derivative to both the function and the surface. So we apply to the field and apply to the boundary. You get this. You can see this is the Lorentz force, and this this difference is the changing rate of magnetic field. Its flux. It's the flux of the changing rate of magnetic field. That's what it is. Give you the circulation of electric field. And the other one is, this is the changing rate of displacement vector, its flux. It's the flux of the changing rate of the electric field. Why do I have to say this correctly? If you put this outside the integral, that means the flux of the magnetic field, its changing rate. Now it's the changing rate of field, its flux. It's just reverse. Okay, so there's a little matter here. So if you stay inside the medium, you have this. But if you outside the medium, those terms are gone. So in the vacuum, you return to the original equation as the walls. But both meet where? Meet at the boundary. So meet the boundary condition. That's what it is. Okay, meet the boundary condition. So those one can be derived exactly from the mathematics. So I present this one equation in the papers here. If you write it generally, you have an electric field, you have the magnetic field correction part, and there's magnetic field and electric part correction. So all this included here. And here, the velocity, I assume in this equation, was varying direction and varying magnitude. So it's called rigid translation. And it can become a slight different format. It's the big D, not the partial T. This is the big T, not partial T. Okay, so this means slight different velocity term, and both include that here, and which include this medium motion in the equation here. So this was the first part of work, but all this is correction part. Sometimes people say maybe it's small. So this is the V cross B correction to the electric field, correction to the magnetic field due to medium motion here. So therefore, that's why medium motion can give you electromagnetic radiation. That's why. Okay. So now if you work on the conservation of energy, through this equation, you can work on conservation of energy. This is the energy increase rate of energy density of electromagnetic field. This is the energy radiated to outer space. Radiation. This is the electric power you supply, electric current. This is the medium motion part. So they have three-way coupling: mechanical driving, electricity, and magnetism. So three-way coupling. You have this three-way coupling that make it, you have one additional term different from the electromagnetism. Electromagnetism is only electricity to magnetism, magnetism to electricity, vice versa. This is a three-way coupling here. If you have no medium motion, this term is gone. So you have this. So I tell you this is based on energy conservation, three-way coupling. Things become a little more complicated, but this is the total field give you this. Okay. Now this is the D called displacement vector, was 1897. A lot more expanded. But this is a field you applied, and this is the medium polarization. That's the medium polarization give you a term. But in our case, have one additional term. What it is? Relative movement of medium. If you have one medium, for example, my phone is moving back and forth like that. If the surface has charge, this motion gives you medium polarization. That term was not included in the displacement vector. Now this medium motion, you have to include that part. So I introduced additional term called Mechano-Driven polarization, called the PS term, the surface charge. So you put on this one, you expand the displacement vector to include another term due to medium motion, which have surface charge due to contact electrification here. As I say at the very beginning, when the people introduced, we use this contact electrification for power generation and sensing. Because the existence of charge and the relative movement one against the other, you have to include this part. Yeah. Okay. So this, of course, including our equation here. So we put this together. So if you have a capacitor, you open part of capacitor, you start having electromagnetic wave radiation. And this is the antenna. You say using your cell phone receive signal because the oscillating field, oscillating electric current give you the field. Oscillating current give you field. Oscillating current give you the field. But now, if the medium also moving, this medium is moving like a shuttle. Besides the current, you have this movement. That's this part, this component. So this component and this component both give you electromagnetic radiation. That's why you see when things are moving, you receive power. At the beginning, the full experiment, I'll show you when things are moving, you receive power. Why? Because this term as well as the other terms. That's why. So we have experimental observation. Even it's very initial, we have this. Just give you a briefing term. So, is this a common approach? Okay, theoretical physics, they use this standard way and use physics law on the station medium approximation. Remember, it's an approximation, it's not exact. Okay, anything on the motion, right? If you say in the universe there's no stationary thing, they say Earth is at 1700 kilometers per hour moving in the universe, but we feel nothing, right? Because we in this middle, yeah. And Earth also rotating, the galaxy is rotating too. So absolutely no inertial frame, precisely speaking. So if you have this on this approximation, use Lorentz transformation, you get the field you observe here. This is the famous relativity theory. You got that. In our case, we use Galileo space. We derive the equation for slow motions. That's good for engineering. Slow means what? Much slower than speed of light. Speed of light is 30,000 kilometers. No, 300,000 kilometers per second. But the speed of light on Earth, if you 10 times the speed of sound, is only 3.4 kilometers per second. So it's much smaller than speed of light. There's no problem by this approximation. So on the non-relative approximation, you can get this part. I'll come to if this is valid or not. So this is written classic textbook, and this is most written engineering textbook. A lot of cases we don't realize one another. I'll come to discussion at the end. So this has been considered a formal theory, but this is used a lot in engineering application, can solve our problem as long as you keep self-consistent. In this textbook, John Stratton written this one, utilized similar thing as we did. You see the V dot, the Laplace operator. This is the term we derive. Okay, so it appears in the English textbook many years ago. In the engineering textbook, also appears. Okay, it appears here and as well here, and also recent papers, people discuss how to use this derivation in engineering for engineering purposes. So we try to solve our problem. In many cases, it may not be exact, but it's good enough for application purposes. Right, so this is the one. So now if you look at if the medium is moving inside the medium, the governing equation is the Mechano-Driven, the Maxwell Equation Mechano-Driven medium case. Inside the vacuum, it is just a standard equation. Both meet the boundary condition. This is the boundary condition. So therefore, there's no problem of exceeding speed of light because inside the medium, the light travel at a fraction of the speed of light in vacuum. That means the speed of light divided by refraction index. Okay, that's what it is here. So therefore, there's no such a thing exists speed of light here, but it's approximate equation inside here and solve our problem for that. So this is the two things, two zones. Inside the medium, this is the governing equation. Outside, this is the governing equation. Both meet the boundary. So divided in the domain. In which domain? So in put an analogy, you can talk about this. This is the case that you have on On Earth, this is what we do. On Earth, what do we do? But in the universe, if the travel, just stand the Maxwell equation here. And you see the whole thing. So my case discussed is engineering application on Earth. I did not need to worry about the universe here. Okay, but in the universe, if you look at the space universe, okay, it's so vast. A star is a particle, is a point charge. Right? It's a point charge. That's why you can treat this one, oh, there's a point charge here, there's a point charge here, because the space is vast. But on Earth, it's not. So it's two on different zones here. But look at different scale you look at that. Okay, astronomy scale. We look at on the macroscopic scale on Earth, or micro scale. So this is so when the theoretical physicists look at the unification of full fields, this most case they look at that, try to be on approach the theory to unify the full fields. Okay. Why do we need to consider relativity in space? On Earth, you see, okay, a bullet is very fast, right? But this is very small compared to speed of light. But in the universe, speed of light is like this, like the universe. From the Earth to Mars, take 180 some seconds for light to travel to get there. In the universe, it's even much slower because it's so huge. It take many years, many light years to get across. So the scale is different. Wow. This is what we consider most okay. Yeah. Okay. So therefore, depends where's your reference frame, or reference frame. Now, let's have some more discussion. I present you the case. Why do we need it? How do we do it? Now let's say look back at the textbook, see what text is written, and see what we can derive from here. The first one is Galileo space and time. Galileo space, time is time, space time. There's no correlation. Like on the universe, your clock is same as my clock. Your clock is the same as somebody's clock in New York. That's what the Galileo space. If you consider relativity, they say, oh, yours has a small difference because the distance. Okay, of course, that's exact say there's a small difference, but for our engineering purpose, that may not be. But for satellite communication, you may need to consider some relative correction for that. But let's for our so in Galileo space-time, is it valid? 1965, it also already answered under two conditions. Galileo space-time is valid. Number one, the moving velocity is much lower than the speed of light. Number two, the spatial variation, that means time variation, is space variation, spatial variation of which is much smaller compared to distance traveled by light during the time difference of this event. That means light travel from here already to the other side of the world, but our things happen in this side of the room. In this condition, you don't need to consider relatives. So 1865 already proved that. So many things on the Earth, we do not have to consider relativistic effect. That's what it means. So much simplified. You don't have to make our life complicated, right? Simplify. So this is the regard Galileo transformation here. The second one, let's see what the European people, that depends on the Galileo space-time. They developed Galileo electromagnetic. Started 1973. I look at most of the textbook we use for teaching electrodynamics was written before then. Landau's book, Feynman's book, even Jack's book, the first version way before that time, was written before that time. But he say this one, he say that Galileo electromagnetism is not a native to special relativity, but is precisely the low velocity limit in the electromagnetism. Right? That's what he say. And he also say, 1 century after seminal work of Minkowski, electrodynamics moving medium is still a subject of investigation for research and should be included in the physics lecture. It's not a list, to my knowledge. Because the textbook we use most was written before this time. So this part was not written here. And he said this. He said, Galileo limits provide an efficient way to analyze a large amount of phenomena studied by both engineers and physicists. So we should include this our teaching. I don't know why was not included. Because the textbook written before that time, most time, probably never changed. You have to look at the new thing they developed. This has been around for 50 years in Europe. Okay. Number two, in this, he wrote this one. In conclusion, the Galileo electromagnet discovered after relative electromagnetism seemed to have to take its place next to the Newton's magnetism. These two theories have naturally a domain of limited value. That means U value here, R value here, both meet at some place. But they, nevertheless, very useful in the practical explanation of the Galileo phenomenon. And that even that time they faced debate. So let's us remind what Poincare on the future of Newton's theory after the invention of special relativity. He say what? The Poincare say that today certain physicists want to adopt a new convention. Those who are not of this opinion can keep the former in order not to disturb their old custom. I believe between us that it is what they will make even for a long time. So they're still going to debate for some time. That's okay. That's what science naturally go. But look at what happens in the world. There's a discussion for that. We have to think about this one. And even lastly, this author, this Rorschach, he said this. Let's I wish that Galileo electromagnetism replace special relativity in common practice. Common practice, that means engineering. That's what he said. Right? So therefore, a lot of things discussed. Now let's look at about Lorentz transformation. Okay. If you look at more, there's this interesting discussion. So on Maxwell equation, Lorentz current, he say, so we recall that the tensor form of Maxwell equation does not secure their tensor contents. They become covariant by postulating 假设 certain transformation property of field function. Then he also say Maxwell electromagnetism in vacuum is already covariant on the Lorentz transformation. Is commonplace in the literature. And then say this Lorentz covariance become if we can construct to be. So they are covariant if we construct it to be. You understand what this sentence means? By postulating certain transformation function. Still have discussion about that. So it's mathematical transformation, but very important transformation for that. But still people say, well, this is you made us do this transformation, so that's covariant. Okay, so this is a many interesting discussion if you look at the book here. The other interesting thing is this one. People talk about relativity as speed of light. They always mean speed of light in a vacuum. But if you have medium, what's the speed of light if you put in a Lorentz transformation? People say it should be the speed of light in a medium. That's good, right? If you have an infinitely large medium, like an ocean water, you can have an infinitely large medium. But if you have this, have a finer object, if a light go through here, what's the speed of light that you put in a Lorentz transformation? Nobody think about this question. Why? Because in universe, each star is a point. Why you think about this? So you always take the speed of light in vacuum as the standard one. But on Earth, it is not. We have a test, we have a size of an object we have to consider. But nobody think about this question. Just take it. Right? So more you look at that, so this is what I found here. Then you look at this one more. This is not a published paper. This appears in this website. They talk about Lorentz invariant of Maxwell equation in matters. The aspect of Maxwell equation that fails to be fully covariant in the presence of matter are the constitutive relations. People do discuss about this case, so we should be open-minded. We should look at this one classical. So we learn from class theory, we expand the class theory, we also develop class theory, which at least was developed 20 years ago. Is there anything new done recently or nothing new? Or people say, this is classical, everything's done. You are not doing physics unless you do quantum physics. Could be. So therefore, something just stimulated us to discuss about this. So I just present to you and see what you think about this. Okay? So lastly, let's look at Faraday's law of electromagnetic induction. Go to my question to Feynman's book. How do you explain the anti-flux cases, examples? Let's go to the equation I derived from Maxwell Equation, Mechano-Driven systems here. Okay? If you look at Feynman's book, table 18.1, he says linear integral of electric field around a loop is the flux of B through a loop time derivative. If you write mathematics, this is it. This is what it is, right? Okay. Now let's look at this one. Another statement is in Jackson's book. Somebody, we learn a lot from this book. Okay. So this is the magnetic flux. If you look at time derivative of flux, give you the electromotive force. I have a lot of study on this recently. I find I have some condition on that, but sometimes ignored by people. In Jackson's book, he discussed the case that he said medium motion means constant velocity motion. Constant velocity motion. So you see x minus vt, this is constant motion. Constant velocity motion. Yeah. And all physics law, all physical phenomena are the same when viewed by two observers moving with a constant velocity relative to one another. That's what written in the textbook here. And then he utilized it, say, well, this is a E prime. What's E prime? Is the field seen by the charge on the medium, on the moving circuit. This is the definition of electromotive force. Okay, so this is the time derivative of magnetic flux over there. Now, if you apply mathematics, this gives you two terms. One's here, and the other term I move to this side is this one. Okay, so now he wrote another sentence. He say, but we can choose to interpret different. We can think of the circuit C and the surface as instantaneous at a certain position in space in a laboratory. This sentence is very difficult to ask what he means. Let me explain what he means. Okay, he means this field has to be something different from the E you observe in a lab frame. He assumed the field observed on the lab, on the rest frame, on the charge. That means if this is the charge moving, you make a reference frame moving with the charge. That's the field you see. This is the field we see by me. I'm not moving. But this equation conditions what? Constant moving velocity along straight line and inertial frame. No acceleration. Also, consider the charge, the unit charge, which is moving velocity, equals the medium moving velocity. This is the assumption on which you can substitute here. You got the standard differential equation. As people say, oh, you cannot change the phase, you cannot expand the Faraday discussion because this. Remember, these are the condition. Nobody think about the condition. But this condition fails if you have a moving medium with acceleration. And especially the unit charge moving velocity is not the frame rate. You look at that. So you look at it. In my case, I say, well, if you have a charge in a system moving, it's the medium moving velocity plus the relative moving velocity. If you put these two together, you substitute to the here. On the right-hand side, this is the mathematical identity. On the left-hand side is the definition of electromotive force. If you approximately assume this is correct for even for accelerated medium, you can substitute this back here. But did not completely cancel. You see, this V cancel with this term, but there's a relative motion with respect to this is there. There's a term remains. So if you put all these terms together, you have two cases. Number one, if you have a thin circuit, like that. On the thin circuits, this linear integral, this term drops out. Why? Because the velocity, the moving velocity of the charge is parallel to the circuits. That's parallel to circuits, and this is absolute zero. That means this term dropped out. You got the differential equation standard. Now, if you have a disk who's rotating here, This term cannot drop out. You have an additional correction here. That's the term explain anti-flux example given by Feynman. This is the Mechano-Driven. That's why I always emphasize medium. What's the medium? This is medium. Medium and motion. And one motion, accelerated motion, is rotation, accelerated motion. If you put this one, you do have the equation here. But in the book, we do not include that part. So now let's look at the here. This is Feynman gave you standard example. Obey this one. And this is the anti-flux rule. Now we can explain why, in this case, you have that included. And this is a good example to illustrate if you have a moving medium, especially you have a structure of the circuit changing, something's different. Something different, especially like a relative motion, something different. Okay. So if you have a fan-shaped electrode rotating a magnetic field, if you according to this standard form, there's no potential drop. Let's say this is 0. But if you mathematically work it out, it gives you this term. Yeah, this term will give you the correct answer. Across here, there's a field drop because this includes the charge motion due to the rotation of the fan. That's the relative motion velocity term. Okay, if your relative move velocity is RW, W is the angular velocity. So this is the term. You calculate that term, you get here. So, in other words, in this case, you see that geometrically there's no flux change. So even the disk rotate, according to this equation, it's not supposed to have electromotive force. But in reality, you measure you do, because this is sliding, and this is a contact sliding. The structure of circuit change. If you do this integral, the charge come to here, and then this disk is rotating until a moment later move to here. So truly integral part is here to here to here to here. So this is the area that includes the magnetic flux change. You do have a term here. So medium motion do give you this one. All right. So all this one, if you look at details here, there's a lot of things you can figure it out afterward, but it's not clearly explained in textbook at all. So relativity means what? Two persons see one phenomenon in vacuum. Special relativity. This is the point charge in the vacuum. Bob said, Alice said. Alice is right there. And what you see from me is same charge, but different field, which is given by relativity. So two persons see one phenomenon in vacuum. That's what it is. But now case is that one person see two medium which have accelerated motion, which have a shape and a size, arbitrary motion. What do I say? So this is the case we talk about. So if you look at the Maxwell equations, is on what condition? Number one, the moving velocity is constant. That means the inertial frame, the force acting on charge in its rest frame and the lap frame is the same. Then you have this. In general, you do not have this. That means you have a correction term. This is what case we talk. That's why I say medium with acceleration. You have acceleration, you have to consider. So things become a little more complicated. That's why I'm going to discuss here. If it's not complicated, why should I bring this question to you? Waste your time here, right? So this is, see, any things have an approximation. We need to tell the student exactly clearly what it is. What it is. And if this does not equal the other one, you have to go some new derivation as I show you. Okay? So if you in a vacuum or in a medium occupied space, you see one phenomena by two persons. If a medium is moving, one person sees two medium here. That's what we're given here. This is for what? For on the low speed phenomenon on Earth. We do not expand this one to the universe. No. This medium have size and shape. If you go outside medium, all this term drops out. So become a standard equation. So that's what I'm talking about. That I want to explain to detail. So all these things written clearly in our book, in our papers. So this is the term. So last boring slides. Why the Faraday law of electromagnetic has to be expanded for moving medium? People say, no, you cannot expand. This is something you cannot touch. But let's look at details here. According to Stratton's book and the final book, this is the integral expression of Faraday's law. I derived this one at the first half. Now look at this one. I give you this Jackson book used a different definition here. I derived a similar thing. Okay, similar thing. But through electromotive force, due to the relative motion of the unit charge with respect to medium, you can get things. Also, if you have a uniform motion, means uniform motion, V equals V0, the two field force are the same. Inertia term, you get this term. And this term, because the moving velocity of charge, total velocity, is the medium motion charge, velocity, and the relative motion. Two put together, you get this left side equal this, and right hand side equal this. These two terms are equal, cancels. But the remaining is this. Okay, here is the constant moving frame, but have a relative motion velocity with respect to medium as the disk are rotating. So if the moving velocity of unit charge is the same as the moving velocity of the rest frame, you get the standard equation here. So this brings me back to our debate, back to April. Okay, back to April. Now let me tell you what was something did not get right in that PPT. Okay, let me just tell you. So is this term relative? Okay, and this, if only on this assumption, the VR equals 0, you go back to what I do originally. So if you do not have a inertia frame, maybe acceleration, this is not valid. Okay, so therefore medium surface boundary have to be included in this one. And so we have to expand the equation. There's no doubt about it. Okay, so this back to our debate that time, and I took two PPT from Professor Wang Chen's slides. He presented this. You can look at all this online, and mine asked the question as well. You can see this almost 4 hours. Include answer question 6 hours. Okay, 6 hours. Now, in Professor Wang's PPT, he say that if you use electromotive force on the left-hand side, you get this. On the right-hand side, you get this. Okay, and they say two term cancels, but a sum will assume on this side, this term, the moving velocity is same as the other one. This have a condition. The reference frame is constant. Inertia frame. Number two, no relative motion of the charge with the medium. That means line, linear circuit. So linear circuit, sorry, this is correct. But you have a disk. This is not always the case. You cannot cancel. That's why the way the things go on. So therefore, I list the condition on which you can do that, on which you cannot do that. So condition is listed. So assume moving velocity of virtual charge is the same as the medium motion, valid in some cases, but not in general. So that's why you have the term I introduced there. So lastly, more interesting part. I go through all the boring part for you. So now it's interesting. Let's summarize. To space and time, relative space and time. They consider space and time are unified. This is a big contributor by Einstein. And a uniform, most cases, special relatives uniform moving velocity in the inertial frame. Remember, no acceleration. But it works for any speed, but in a vacuum for charged particle. Not a medium with shape boundary. That's very difficult to do in that case. Because what's the speed of light? We have a part of medium is something different. If light go through, what's the speed of light? What's the transmission? It's different, okay? So this is the relative, but it's the absolute speed and time, which first one is Galileo's electromagnetism, has been developed for over 50 years in Europe. But in China, there's almost no work on this part. I don't know why. Okay, so you look at this one. This is for engineering application. We don't have to be unified for forces, but it work for us. So I think like a biotask is working. Let's do energy and sensors. Use this one. What we can develop. I'm not worried about unified full force. That's no I cannot do that. I can only do simple thing. Okay, so absolute space time. This is the first one. The other one is our Maxwell equation for Mechano-Driven slow moving medium with acceleration. time variation, space variation, all inclusive. So this one I have it very clearly in the papers for that. So I wrote these papers, sometimes very hard to read, but if you have interest, I will happily explain to you. So all this one's a review paper on a TNG, and this material today, the first paper, and it was this paper caused a debate, and this was the recent one. There's two in Chinese because I wrote one, so easy for you to understand. Otherwise, I truly talk to foreign language to you. So okay, so and most recent online here is we are doing this step by step. Okay, so all this gives me experience that we learn a lot from this discussion, from this debate. Some question we never think of hard, we never think in depth. We always say, oh, this is written text, you cannot change this one. But as new phenomena observed, we need to look at new phenomena and figure out what new thing can do. They say, well, this is not important. What you do is not important. Who knows? Let me tell you. 1831, Faraday invented electromagnetic induction. 3 years later, Lenz developed Planck's law. 25 years later, Maxwell developed Maxwell Equation. This is the final form until 1897. This all remained theory until 1888. Hertz saw the electromagnetic wave. And I will tell you what Hertz said when he saw this electromagnetic wave. Okay? More than 55 years. 55 years. Maxwell only lived for 49 years. He died in 1879. Before he died, he didn't know his theory was correct or wrong. I bet he felt very stressful. Right? People, which was not accepted until Hertz saw them experimentally. But he did not know. He already passed away. Very pity. And Hertz did not live long either. Let me see what Hertz said. From the famous quotation, Hertz only lived to 1894, 8 years after he discovered electromagnetic wave. And he say what? He said, it's of no use whatever. Look, this is just an experiment that proves Master Maxwell was right. We just have this mystery electromagnetic wave that we cannot see with our naked eye, but they are there. They don't believe this is useful at all. I just saw these things. Maybe I don't think this is useful. That's what he said. And he lived too short, not long enough. He did not see this change the world. From this one, we should learn a lesson. Something you think today is not useful, in the future you cannot say which is not useful. How do you know? Can you live with 50 more years, 100 years more? Could be. Yeah, young people will. You're going to say it. Right? So be open-minded. Science needs development. Science needs a new experience. So I can X. This X represents impossible, possible, unknown. So look forward. I don't know what happened. 2006, we used Physical Electromagnetic Induction, published first paper. I never know this paper going to lead me for the next 20, 30 years. Never know. 2011, the TNG was published first paper. I remember that time we had a lunch with Alice in Italy. And I tell her this is important. I was trying to motivate you. Say, let's do this. And she did. She came back right away. And I think I gave you a talk in your group probably a month late, something like that. And they did beautiful work afterward. Okay. Then last year we developed this one. You ask me what's next. I'm working on it. Give me time. Give me some resource too. We can do that. Don't tell me, this is useless. This is not useful. How do you know? Don't say that's useful, not useful. Let's be open-minded. And probably may not be very useful, but let's look at this. All what I say today may not be 100% correct, but I bring it here as a debate and discussion. You can judge yourself. See, what I tell you is make sense or not. All things published in the paper, you can criticize and it's okay, but science needs a discussion, need an open discussion. need to truly look for real things, right? Okay. So this is so go back to what Hertz said. The rigorous of science requires that we distinguish well and unwrapped figure of nature itself from the gay-colored venture with which we clothe her at our pleasure. Children, that's what we do. Okay, so therefore, I'll be more than happy to discuss with a lot of people, especially if they don't discuss with me, didn't question me. I did not think this far, so I thank them for questioning me. So look at forward. Moving medium on Earth. Inside medium use the equation with the right. Outside medium use standard. Both meet the boundary, and this is the boundary condition. And this whole thing should be solved. For that, I mean, for this low speed case, but we're going to develop a lot of experiment to prove this. But at least the full experiment I illustrated at the very beginning, already observed, published for that. So, conclusion already very clear. Number one, in a vacuum, there's no need to expand the Maxwell equation, regardless if there are medium or not in nearby. So let me see. If I consider electromagnetism inside me, you are moving or not, it doesn't matter. If I, no, I'm sorry, I did say wrong. If I consider electromagnetic wave right in a vacuum, I'm moving or not, it doesn't matter. But our boundary conditions change. But if you look at electromagnetic wave inside me, if I'm moving or not, matters. That's what it is. So inside the medium matters. If I do this, matters. If you look at things outside here, if I'm moving or not, doesn't matter. That's what I say. The total solution to meet at the boundary. Okay? So every electrodynamics Maxwell object on Earth for engineering application, one need to use the Maxwell equation for a magnetic-driven system. Three-way coupling, Mechano-Driven, electricity, and magnetism. Lastly, we'll also expand the displacement vector into the Mechano-Driven polarization term, which is also new. So therefore, this is my basic conclusion for that. So if you look through this one, I think could offer something interesting discussion for many people, and also bring something to learn for our teaching electrodynamics. I don't believe our teaching electrodynamics bring anything new developed in Europe for the electromagnetism. They rarely talk about this problem. So something to think about the teaching too. Okay, let's use this one to encourage all of us. Einstein says, formulation of a problem is often more essential than its solution, which may be merely a matter of mathematical or experimental skill. Formulation, 公式化. To raise new question, new possibility regard all problem from a new angle requires creative imagination and make real advance in science. All the problem look from new angle. That's real science advance. That's what he said. Most importantly, last two, when you meet difficult, let's say this is from Agassi, from the famous Nobel Museum, have four banners. See the four banners, this is one of them. Say every scientific breakthrough goes through three stages. First, people say the conflict with the Bible. Next, they say it has been discovered. Nothing new. 50 years ago, people know that. Last, they say they always believe it. Remember three stages. And this is a philosopher, Schopenhauer, he said even more said, all truths pass three stages. First, it is ridicule, 嘲讽 must be wrong. 太可笑了，老师还修改这个方程，还扩展这个方程组 ，this must be wrong. Then it is violently opposite. 网暴。Right? Third, it is accepted as being self-evident through stage. The philosophers say, it's not me. So do remember this, when you meet difficulty, don't be afraid. Let's discuss for that. And then say, well, 网暴. Right? Let's respect science. You can do that. Use this one to encourage yourself. So when you have a difficult, everybody goes through difficult. Regarding to business, to investor, science, whatever. If you want to do something good, great, you must go through. It could take a few years. It could 10 years. Who knows? That depends how things develop. But this is true. This is all summary here. Remember that. I use this telling myself. Okay. So, lastly, I want to congratulate you for this formation of this clubhouse for the scientists, world scientists, connect the world and the universe and the galaxy too.
Yes.
And it's I want to thanks Alice for did such an outstanding job. Her work, her leadership, her creativity, and the team, and you folks all did a tremendous job, which is phenomenal. I'm astonished when I come to this room. My eye was blurred with many so new things. I still have shiny in my eye right now. So this is for the science, for the spirit of science, for the truth of science. Thank you.
Thank you, Professor Wang. Actually, I really believe that Professor Wang's, the conclusions were important for everyone, not only for his story about all these, equations today. Yeah, I
Too many
think no one sleep. You see, everyone was very excited here, so don't worry about
Because
it.
we have this coffee for them.
Yeah, they also looking for beers. Okay, here I have a very encouraging message from a team in New Zealand. They send a message to me. He say, Alex, I'm so glad for this new setup. It seems excellent. I guess it's also a sign that everyone can go together. Yeah, I hope this is a sign everyone can go together. So you should tell Professor Wang, yeah, I'm the 10,001 group was follow his work. Yeah, so but because I didn't publish a paper, but I follow his work, so that's very encouraging. Okay, yeah, now I think we have time for the questions. Yeah, before we go to the audience online. So, who is the first one? Okay, please, Yuhan, come here, please. Yeah. Okay, I'm proud of Yuhan because Dr. Yao Yuhan, he was 10 years ago, he was a winner of ICANN, the contest.
Wow.
Yeah. Okay,
You
please.
see, this
Yeah.
is the training from beginning
Yeah,
to all the way your success.
Yeah, thank you so much for your insightful presentation, and thanks again for Dr. Zhang to invite me here. And before I ask my question, I'd like to share a little story. I actually attended one of your seminars in Los Angeles a few years back.
2 years back.
It was a large.
2 years group or 2 years back. I mean,
I cannot remember. During my PhD time there,
that's quite a while ago.
I attended University of Southern California, and I remember it was a large hall. You are here near the stage podium as always, and it was way back there. So I tried to ask the question back then, but I was not given a chance. But today, thanks for this club of exclusivity, now I do have a chance to do a face-to-face question and answer. So I know that you discovered two important original work, the piezoelectronics and the triboelectronics. And personally, I'm very, very intrigued about the story behind these two original discoveries. And was that like a eureka moment? Or that was like you knew something by theory was there and you keep striving for that? Like, which way was it?
Yeah, thank you for this question for that. And sometimes just an idea. Let me tell you, how do I get the piezoelectronics idea? Okay, it was 2006. I was participating in a conference. So in Taiwan, on the way fly back to Atlanta, I was trying to think, how do I summarize a few things discovered? So I was draw the circle. 3 circle ideas came from there. I'll use a piece of newspaper, draw that. I said, what is this name? I said, well, piezoelectricity and semiconductor, probably called piezoelectronics. So I called a name. It was around the Thanksgiving time. So when I got US, then was MR's conference. I had an invited talk. So I went to invited talk. I changed my title. So I changed the piezoelectronics for that things. After I gave the talk, there was a reporter from chemical engineering news. Say, hey, wait, tell me what is this? I said, well, I don't know exactly what it was. So I explained to her said this, I think, is piezoelectricity can serve the gate for transistor control. This is just my idea. I don't have the theory yet, but I'll phrase it. She wrote a half a page of what I told her. It was first on the paper was in the Chemical Engineering News. I still have the shots. And those first came up to now, become third generation semiconductor all the way up. Sometimes just things pop up.
Just
so you never know. But the important thing is you got to phrase it and publish and keep calling it and keep working on it. If you only publish one paper 10 years ago, who remember? Nobody. Right? You have to keep working on it and people slowly catch up. So now I saw a report from the Sandia National Lab. They put piezotronics in parallel to spintronics and quantum tronics in the era of post-FET time, field effect transistor. This is a high regard by our work, but it was first came 2006 December, that time. And January 2007, I wrote a 2-3 page work, published in Advancement. That was the first one I wrote the idea, and still valid. So there's sometimes you just suddenly something came to mind. The other thing I'll tell you this, in the tree, I used the tree summarize on work, right? The tree I did this day, although many people came out one Sunday. I was jogging, came back, have a shower. So how do we sum our work? Use one thing so people remember. They suddenly said, well, how about a tree? So I online I grab a tree and put different fruits on that. I said one tree can different fruits can be pear, can be apple, can be orange. So I put one. That one published in the MRS Bulletin, the first version. The new version I use right now. That was after many years, but it was just something came up. But you got to be brave and publish and consistent on that, and then become an important event. So nothing's important until you work on it and make it.
Thank you so much.
Very great. Yeah. So yeah. Any other questions? Okay, please. Yeah. Stay here.
So
Before
this picture was 23 years ago.
But look at exactly the same. Yeah.
Kind of change.
Even more handsome. Yeah. So I have a question from online here as Wang Yishu. He asked about for the triple electrical generators like this. Yeah, so the it's not very stable because the surface, always get some charge. It should be very active. So this was not very stable. So how about you can explain this by the current display current?
Oh,
yeah.
Good.
Okay, please.
So let's do this one. This is a medium moving. So the surface charge on the surface. So if you're moving back and forth, let's say at here you have the charge over here, you calculate the field. If you slide out, the charge give you new field. Time variation of this one give you the space distribution of field. The time derivative of that field is the disciplinary current. That trick the electrode give you output. So that called disciplinary current. A time variation of electric field plus the medium polarization field inside medium give you the current called disciplinary current. That's what it is. The student can read the review I wrote on that can give more in depth about that.
Yeah, cool.
It's called disciplinary current.
Okay, very, very great. So any more questions?
Displacement current.
Okay, so here we also Meng Di, come here, please. Yeah. So when you do triple generators, Meng Di was not come to the college yet.
Oh, yeah, that's exactly my question. Maybe I was wrong, but I want to point maybe mistake in your slides. In your slides, you say that in 2011, that's the invention of triple electric nanogenerator. I think maybe you submit the paper in 2011, but the paper got published in early 2012. So that's the time I joined Alice Group as an undergrad and do my research. And I started my PhD in 2012, September. And in early 2012, I joined her group. And at that time, I saw your paper. That's the first paper of triple electric nanogenerator. and I did my PhD research focus on that area. So my question is, for your case, you expand the Maxwell equations, and in my opinion, when you establish a new theory or fix or expand a theory, there will be many new opportunities and new applications. So what's the new applications that you envision after you expand the Maxwell equation? What's the immediate application and what's the future, the long-term applications?
Okay. Very good question. Thank you, Mundi. First one, let me explain to you. So the work on TNG was finished in 2011, first work. And I submit to a journal. Next day, rejected. But the day I looked at the date it was rejected was 9/11. I said, well, bad day, 9/11. So I submit to another journal. I don't want to mention the name of the journal. I submit a journal. After 2 months review, reject. 3 referees. One referee said, terrific, great. Then the other referee said, wow, this group, I recall his work was questioned by a German group back in 2007. And they published another thing. I don't believe it. So bring the old stories. It must be rejected. And then the third referee said, good, perfect. So the editor rejected me. So I wrote a rebuttal letter. I told the editor, I say, this is, to my judgment, this can be an important discovery. And I think publishing your paper in the future, you realize it's not only a high side paper, but also bring a lot of things for people to study. So I did write. I still have a rebuttal letter. And they said, oh, okay, look at you. You have been a good author for us for some years. Let's reconsider. After a month and a half, reconsider, reject. By that time, I have the second paper, third paper already finished, but the first paper has not published. So I have no way to go but to publish in Nanoenergy as a paper. That's the first issue of Nanoenergy. I just launched the journal in January 2012. That was the last paper in that issue. So I put it in. Of course, I was the editor, right? Yeah. Turned out to be a big discovery, right? But you never know about that things. That means what I use this example to tell students, not always the greatest work published in Nature Science. May not be. Time will prove it. Time will prove it. So this is to answer your question. First question. What's the second question?
The second question is, what are the immediate applications and future applications?
I try now to do more numerical calculation and new experiment design. I hope you use this one to verify the terms we introduced there. In some case, which can quantify the TNG output as well as the electromagnetic radiation. So this needed some time, but I will do it.
Okay.
Yeah.
Thank you.
Everything needed time, resource, and personnel. And most important, the smartest students. That's what they need.
Okay, I'll come over. This was a call for the students. Okay, Chen Jiang, come on here, please. Yeah. So we do have a lot of people who have questions. Please.
Professor Wang, I think I saw in your presentation there is an experiment that show when a researcher rub a surface and there is a device got some signal from maybe 10 meters away. And because I'm majored in electronics and the circuits, so I'm very interested that the signal you got from the waveform is very high quality. Maybe sometimes we think it's filtered. So because the rub surface is a very random process, and I think it's very weird that you got very good signal.
You know, the advantage of TNG is this one: slow motion give you high voltage output.
Yeah,
the voltage signal high, so the quality of signal is better than piezoelectric and other signals. So you have a slow motion like a voice tricking. That
so you mean some native or nature 本真频率 I mean Okay, nice.
Oh, let me say,
Yeah.
you talk about the intrinsic frequency. That's the resonant frequency of
Oh, yeah,
circuits.
you just.
That's the standard way to do it. Ours is based on mechanical treatment, the signal.
Yeah.
That's the frequency that send me out.
So I'm very interested in that.
Let's
I'll
look at
follow
that.
you. Yeah.
So that's why the mechanical tricking give you the radiation at its own tricking frequency.
Yeah, I think it should be.
Yeah.
But you got a signal, maybe very narrow banded. So I think maybe there are the receiver filter at the device side. So I think I don't know. So
Let's look at details.
Okay.
Okay, we can discuss about that. So we need people like you who are very expert on electronics and here, and this provide a native way, a different way for you to think on what case you can utilize this approach.
Okay. Okay.
That's what the discussion is beneficial.
Thank you.
Yeah, cool. I think, we look at Professor Chen Jiang, we can feel that this is very safe place because he wears this mask. Yeah, so we are very good for the, COVID control. So any other questions here? Okay. Yeah. No. Yeah. Well, we get questions from Africa. Yeah.
Africa.
Yeah.
All right.
I'm so proud of that for ICANX today. For the Africa MRS. So yeah, they send out the flyer of your talk. So a lot of people was here. This was Nakazu. So yeah, I hope I pronounced rightly. It says that Professor Wang. Yeah. So in our place, it's really hard to get enough, electricity. So for the TNG, is that possible to help for our life?
In Africa, we do have a project before. Is because in Africa, one of the things that people don't have light in the evening.
Yes.
So how can you get a lighting for their daily life is important. So we can use the wind, can use the motion in environment for generate lighting for them. So it can be utilized for that. And we had this project a few years ago. Why we stopped for that? Because for mass production, if we do research, but for mass production, we don't have the capability for mass production. They need how many units a day? We could not do that. But I think we could look at this one and possibly for this poverty, solving poverty in that area. So
Yes.
this is do have one solution for that.
Yeah. Okay. Very, very great. I'm so proud of that because I can really reach
Africa.
globally
Yeah,
Africa.
global.
And last week we have speakers from Africa, so I have several scientists that join that. So now it's very popular program there. So yeah, many students was following all this. I can talk. So I think a lot of collaborations can be coming out in the near future. So really, really great. So I think today, yeah, we are so happy to have Professor Wang here, and I'm so excited because that's the first time I can deliver the certification to you in person. Yeah, yeah,
Thank you.
indeed. Yeah. Okay, great. Yeah, we shall take a photo. So, I think you got this third times, right? This is the first time in real.
I take very as a treasure on my shelves, and I'll put it here. I will keep me a good memory because give it very different talks.
Yes,
If
yes,
I give you a
it
talk
is.
on TNG, that's probably I have too many certificates.
Okay, thank you very much. Yeah, Professor Wang, we're so proud of that. Our first, show in this ICANX club is so successful, and we have many, audience online. We have many people here. Yeah, we hope next week we also can have, a lot of people here because next week we're going to have Professor Nicholas Peppers. I want to highlight it's not only Professor Peppers is a super scientist because, next week he came here as in purpose is because our Teachers Day. So Professor Peppers is one of the best teacher in the whole world. You couldn't believe that in his group already nursing over 1,000 students, postdocs, visiting scholars from his group. So we're so proud of Professor Nicholas Purpose. Next week, we're going to have a big team here and hybrid online and on-site. So I hope we can keep you here. And welcome to ICANX. And this was the best place for science. So ICANX, Connect World and Universe. See you next week. Bye-bye.
Thank you.
See you.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以